So we are back. We are still continuing in chapter 3, and this is the, I guess, third set of examples that we have, or section 3.5-3.6, example set 2, I believe is what I called it. And before we get started, I just want to again review, okay? These equations we have to understand are from an axial loaded specimen, okay? It can be tension or compression, but I have a force P that's acting through the centroid, and this could be part of a system, right? It could be one of many cables, and it has that internal force, okay? It's going to have an original length right there, and this is also going to be the direction of our longitudinal, okay? So I'm going to write right here, longitudinal is in the direction of loading. So when I get this delta, okay, delta, okay, what is delta? Length final minus length initial. I'm also going to be able to get this strain, and that's the longitudinal strain, okay? As it gets pulled, our cross section is our lateral. It is perpendicular, okay? It is perpendicular to the load, okay? So looking at this whole system, I can see that I have stress is P over A. This is going to be our force and our area, okay? We can relate then the stress to deformation using our modulus of elasticity, which is that slope, okay? And I know that strain, so I want to remember that this is the longitudinal strain that I'm using here. This longitudinal strain equals length final minus length initial over length initial, which is delta over L. Okay, if I know the longitudinal strain, I can also, using Poisson's ratio, okay, calculate the lateral. So we have this very nice spectrum. Sometimes you might know this part or part of this part, and you might know the delta, and you're going to be asked to find other information, okay? Sometimes you might know the lateral strain, like we will in this next problem, and I want to go back and figure out the pressure or the stress that caused the whole thing to happen. So this spectrum right here, it's very, very important to understand. You're going to know different pieces of this puzzle, and you're going to have to figure out, do I need to work to the left or to the right to figure out the information that the question's asking me. And I just think it's important to understand this kind of like spectrum-y way to look at your equations, okay? This, again, is shear. So if I have a block, okay, and I have a force that's acting parallel to that cross-section, I know that shear stress, okay, shear stress is that shear force divided by cross-sectional area. Okay, and as it slides or skews, I can calculate shear strain. Okay, I can calculate shear strain. So we have the same type of relationship. I am going to have a force, that's my shear force, across this area. That's my shear stress. When I look at the different material types, I can then calculate gamma, which is the shear strain. And I know that shear strain has to do with this angle change, okay? So I can work in the same sort of spectrum. I could be told something over here, and I could go back and say, well, what is the actual shear force that causes this to happen? So you just need to understand axial versus shear, and then understand the equations within it, okay? This relates the two together. Okay, so let's get started. We have a plug with a diameter of 30 millimeters that fits within a rigid sleeve of 32 millimeters. Both the plug and the sleeve are 50 millimeters long. Determine the axial pressure P that must be applied to the top of the plug to cause it to contact the sides of the sleeve. Also, how far must the plug be compressed downwards in order to do this? The plug is made from a material, blah, blah, blah. Okay, so I have a plug. Okay, pressure. What does pressure mean? We haven't talked about pressure. Well, I know that pressure has units of, because I think of a tire, of PSI or KSI or a Newton per meter squared, which is a Pascal. And so it's just telling us that the pressure is basically that stress. It's the same units, force over cross-sectional area, okay? So I need to know basically same units of stress, and I know the material because it tells me, and so I can relate that to strain. I'm also given Poisson's ratio, which relates lateral and longitudinal strain. So let's draw our free body diagram. Remember, always start with those. So I have this plug, and I'm just going to kind of cut this thing in half. I'm going to slice it in half so I can see what's going on here. And it has an original diameter of 30 millimeters. I also know that my plug is 50 millimeters tall. Okay, and this plug fits into a sleeve, which again, not the prettiest of pictures, but you get the point. So we can see in here, okay, there's my sleeve. Just kind of darken that in so you can see where I've cut. Okay, and then here's the plug. And the sleeve has an inside diameter of 32 millimeters. And I want to push down on this plug with pressure until the plug meets the sides of the sleeve. Okay, so looking at this, I have a starting length, I have a final length. Okay, this is going to be my original diameter, and this is going to be my final diameter, and these are lengths. So if I have changes in lengths, I can calculate strain. And what I need to understand is I'm pushing down, it's causing expansion. This cross section is perpendicular to that force, so this is my lateral strain. Okay, so if I can find the change in length here, my lateral strain, I can come back up. Can I calculate, if I have lateral strain and I know Poisson's ratio, can I calculate longitudinal strain? Absolutely. If I calculate longitudinal strain and I know the material property, can I get the stress? Absolutely. If I know the longitudinal strain, can I also calculate the amount that I'm pushing down? And so this is where it's just going to be super, super, super important at this point that you understand your vocabulary. Okay, so let's just start. We're going to start over here. So I can start with that my lateral strain. Okay, my lateral strain is length final minus length initial over length initial. So I want to push it so that it has a diameter of 32 millimeters. It's starting out with 30 millimeters. I'm going to divide that by my original of 30 millimeters, and I can get a lateral strain. Okay, I can get a lateral strain, and look, it's working out positive. If I 32 minus 30 is a positive value, I get a positive strain of 0.06667 millimeters per millimeter. And that makes sense. It is getting larger. So what do I know about the length if I'm pushing it down? I know that the length is going to be getting shorter. Okay, so we'll get to that in a minute. So I now have this lateral strain. And if I know lateral and Poisson's ratio, I can get my longitudinal strain. So let's work with that. Poisson's ratio is negative lateral divided by longitudinal. So my longitudinal strain is going to equal negative lateral divided by Poisson's ratio. I'm just rewriting that equation. So I have negative 0.06667 millimeters per millimeter divided by 0.45, and I get that my longitudinal strain is equal to negative 0.1481 millimeters per millimeter. Now, does it make sense that we're negative? Absolutely. If our diameter is getting bigger, the height is getting shorter. We are literally, look, you can see we're pushing it down. It is going to get shorter than 50 millimeters. Here's our original length. We're trying to find that final length so that we can get that delta, the amount that we're having to push it down. This is where a free body diagram will save your life occasionally because you can start filling in the holes. Okay? So I now know my longitudinal strain, and strain equals length final minus length initial over length initial. I have negative 0.1481 1481 millimeters per millimeter equals my final length minus my initial length divided by my initial length. So I'm going to multiply 50 times negative, so that's going to be a negative value. I'm going to add 50, so I'm going to end up with 50 millimeters minus, okay, 50 times 0.1481, and this is going to equal that final length. So my final length is 42.595 millimeters. So the change in length is final minus initial, 42 minus 50, and I get a change in length of negative 7.41 millimeters. So I can just say that I'm going to be pushing down 7.41 millimeters, and I'm pushing it down. Does that make sense? Easy peasy. Now I also need to figure out, well, what is that pressure? Well, I have found, okay, that I have this longitudinal strain, and I know that stress equals E times strain. So stress equals 5 times 10 to the 6th Newton per meter squared times, where's that strain? Longitudinal. Negative 0.1481 meters per meter. And when I multiply this out, I'm going to get negative 741 kilopascals. Well, I'm already saying it's pushing down, so is it pushing down negatively? No, this is letting me know directional that I'm in compression. This is letting me know compression because I got shorter. I already know it's in compression based on the problem, so I can just say then that stress is equal to 741 kilopascals. Okay, and with this problem, it's pretty simple. I have one thing going on, but think about some of the other problems we've had where maybe we have multiple wires. So if I have multiple wires or I have multiple rods, right, they're all going to have a Poisson's ratio. They're all going to have lateral and longitudinal strain. They're all going to have, if they're different materials making up the rods in the system or the cables, they're all going to have their own spectrum. So for each individual piece in our system, they will each have their own spectrum that you have to work forwards or backwards on. So I hope it kind of helps to think about, you know, I call it the spectrum, to think about the spectrum and what you do know and how to check forwards and backwards to get where you need to go.